Let us study the quantum theory of Raman effect. Let us consider a molecule of mass m which is moving with energy EP and velocity v, that is colliding with a light photon h mu, and suppose it undergoes a change in its energy state as well as its velocity. So the new energy state is EQ and new velocity is v dash. So we will be applying the law of conservation of energy. So EP plus half mv square plus h mu, that will be equal to EQ plus half mv dash square and hv dash. That is the rate of change of velocity. Now in this, the rate of change of velocity of the molecule is practically negligible. So this will be negligible. So what is left is EP plus h mu, that is equal to EQ plus hv dash. From this we will find out what is the value of v dash. V dash is equal to v plus EP plus EQ upon h. Now this is nothing but the rate of change of velocity. So v dash will be equal to v plus delta v. Now there are different cases, that is when EP is equal to EQ, the frequency difference delta v is 0. And that is in that case v dash will be equal to v. So that is known as the Rayleigh scattering. If EP is greater than EQ, then v dash will be greater than v. That will be the anti-Stokes lines. Third case is when EP is less than EQ, then v dash will be less than v. That will be the Stokes line. So in that case, the molecule has absorbed some energy from the photon, and consequently the scattered photon is having a lower energy. So when we talk about the change in the intrinsic energy of the molecule, that will be governed by quantum's rule, that is EP minus EQ is equal to plus minus NH mu c, where n can be 1, 2, 3 extra, and mu c is the characteristic frequency of the molecule. So when n is equal to 1, v dash will become equal to v plus minus vc. So the Raman, this shift in the frequency, as you can notice here, v minus v dash, this is nothing but the Raman shift. Now in case of pure rotational Raman spectra, if you see the selection rule, the energy of the rigid rotator, as we know, is given by this equation, is square upon 8 pi square ijj plus 1. So selection rule for the Raman spectra, rotational Raman spectra, that will be 0 and plus minus 2. So when we will put the value when j is equal to 0, when j is equal to 0, the scattered radiation will be of the same frequency as that of the incident radiation, and then it will become what is known as the Rayleigh scattering. And when j is plus minus 1, then it gives you what is known as the Raman shift. When j is plus 1, that will be the Stokes line, and when j is minus 1, that will give you the anti-Stokes line, that is the line of shorter wavelength. So in this case, I am taking the value when j is plus 2. I will put the value in this. So I am getting 2b 2j plus 3, where b is again h square upon 8 pi square ic, and when j is minus, then delta v, I am getting this, and this is the wave number of the corresponding spectral lines. This is how the spectrum will look like. The frequency of separation of successive lines will be 4b, whereas it is 6b for the first line when you put the value j is equal to 0. So you can see here, these lines, they have a separation of 4b, but the first line has the separation of 6b. Now let us come to the vibrational rotational Raman spectra. Now it is possible to predict theoretically that the vibrational and rotational transition can occur simultaneously. So you will be applying the selection rule. This is for the rotational, delta J is equal to 0 plus minus 2, and this is for the vibration, that is V is equal to plus minus 2. The in diatomic molecule, the vibrational rotational energy levels they are given by, you can see here. Now in this V is equal to 0, 1, 2, J we are putting 0, 1, 2. When this is in terms of frequency, so when you apply selection rule, when J is equal to 0 and when J is equal to plus minus 2, J is equal to 0, J plus and J 2. So wherever there is 0 J, you will be putting the value 0 in this plus 2 and in this minus 2. So after solving that, you are getting these values. Now when J is equal to plus 2, that is known as the S branch. When J is equal to minus 2, that is known as the O branch. And when J is equal to 0, this is known as the Q branch. So you can see here S branch, Q branch, O branch. So this is how the spectrum it will look like. Let us talk about the resonance enhanced Raman scattering. So this is first the standard Raman spectra, in which these are the Stokes. This is the virtual level. This one is the ground level. We are talking about the vibrational energy levels. So this is the ground level. This is the first electronic excited state. This is the virtual level. So these are the Stokes and these are the Anti-Stokes. If the wavelength of the exciting laser is within the electronic spectra of a molecule, so what happens that some of the intensity of some of the Raman active vibration, it increases by a factor of 10 raised to 2 to 10 raised to 4. So there will be resonance generated. Now this was the Stoke Anti-Stoke initially in the common case of standard Raman spectroscopy. Now this is the Stokes and Anti-Stoke line after resonance enhanced. So such type of spectroscopy is known as resonance enhanced Raman spectroscopy, and it does not begin at sharply defined wavelength. In fact, enhancement of 5 times or 10 times is commonly observed if the exciting laser is even within few hundred wave number below the electronic level of a molecule. So it is observed in molecule which is possessing vibrations that can be resonately enhanced. The resonance Raman effect, it takes place when the excitation laser frequency is chosen in a way that it crosses the frequency of electronic excited state and then resonate with them. Intensity of Raman band which originate from electronic transitions between those states are enhanced 3 to 5 orders of magnitude, and not all the bands of spontaneous Raman spectrum are enhanced. The so-called the chromophoric group, which is responsible for molecules coloration, they experience the highest level of enhancement since they have the highest level of light absorption. The highest intensity of resonance Raman spectra is observed when the laser frequency equals to the first or second electronic state. Therefore, tunable lasers are most appropriate choice for this resonance Raman technique. Although even when the frequency of the laser does not match the desired electronic excited state, an impressive enhancement of Raman signal occurs. Now let us talk about the CARS, that is Coherent Anti-Stoke Raman. It is another type of non-linear Raman, and instead of using one laser, two very strong co-linear laser, they irradiate a sample, and frequency of first laser is usually kept constant, and while the frequency of the second laser can be tuned in such a way that the frequency difference between the two lasers exactly equals the frequency of some Raman active mode of interest. So this mode will be only extremely strong mode of Raman's signal. And in this case, monochromators, they are not required. Wideband interfere filter and detector behind the filter will be sufficient. So in this you can see two lasers with frequency V1 and V2. They are interacting coherently, and because of the wave mixing they will produce very strong scattered light of frequency 2 V1 minus V2. So if the frequency difference between the two lasers is equal to the frequency Vm, of the Raman active rotational vibration or any more, then strong light of frequency Vi plus Vm will be emitted. About the instrumentation, it will be having a laser source. This is the sample cell. Then wavelength selector will be there, radiation transducer, and then the recording device. Let us talk about the advantages and uses of Raman spectroscopy. It is highly specific. You can analyze the aqueous solutions. You can analyze the organic and inorganic part. No sample preparation is required. It is having a wide concentration range and non-destructive method it is, and it is compatible with common window. So it is a very important tool in the chemical and structural analysis, and we can easily identify the unknown material.